Welcome to the Namboodiri Lectures. How many people know about the Namboodiri Lectures at all? Namboodiri was a student of mine about a half-century ago who did his thesis and died in a car crash about a week after defending his thesis. His parents donated money to set up this lecture series, and it's been going on for about a half-century now. It's quite a few good speakers, to put it very mildly. Welcoming Oscar Randal-Williams from Cambridge University, one of my favorite places. And we'll talk about symmetries of manifolds.
Thank you very much. You invited me to give these talks. So today's one is, as you can see on slides, and is a little more colloquium-ish. And then the next two talks will be a little more details-based. And I want to give some idea of why one of the theorems I'll mention today is in any way plausible. That's basically the goal of the next two talks. But the goal of today's is to tell you some bigger picture things. So I want to talk about symmetries of manifolds, and I've thought about, so that means like automorphisms of manifolds in whatever category you're thinking about, homeomorphisms or diffeomorphisms or whatever. And I've thought about that kind of thing for a long time, but normally about symmetries of very complicated manifolds, like genus G surfaces where G is very large and so on. And the new thing is that I want to talk about symmetries of very simple manifolds, like, for example, Euclidean space. So this character will show up a lot, top D. That's the space of homeomorphisms of R to the D to itself, given the compact open form. Okay, so this will show up a lot. So that is a space of symmetries of the most basic possible topological space, the most basic possible manifold. So there's another one that will show up a lot, which is now the diffeomorphisms of the D-dimensional disk. There's a small caveat here, which is whenever I have things with boundary, I will assume that they're the diffeomorphism, they're the identity near the boundary. The diffeomorphisms of a disk means the identity on some open neighborhood of the boundary, and the topology in this case is a little different. It's convergence of all derivatives. So not just pointwise convergence, but convergence of all and these two things have obvious cousins. Like, why didn't I start out by saying diffeomorphisms of Euclidean space? And why didn't I second that by doing homeomorphisms of a disk? And the reason is that those have, they're perfectly interesting, but we know everything there is to know about. In particular, homeomorphisms of a closed disk is just contractible by the outrageous trick known as the Alexander trick. It's you take the homeomorphism of the disk, which is the identity in some neighborhood of the boundary, and you make the neighborhood of the boundary where its identity bigger, pressing the support of the homeomorphism to a smaller and smaller disk. And at time one, you just get rid of it completely. And pointwise, that does convergence. So in the compact open form, that does convergence. And just gives a canonical contraction of the space of homomorphisms. In the case of diffeomorphisms of Euclidean space, there's a different scaling kind of limit you can take. Instead of scaling inwards, you can scale outwards. And then it's the definition of the derivative, is that if I take a smooth map and scale it outwards, at time one, that converges to its derivative, that's it, which is a linear map. So the space of smooth diffeomorphisms of R to the D is just homotopy equivalent to the D by D invertible matrices by taking scaling outwards. And then you can do, I mean, the Gram-Schmidt process tells you how to take any D by D invertible matrix and make it be an homotopy. So it's equivalent to a compact Lie group. And let's just agree that we know everything there is to know about compact. So these are perfectly interesting, but they're sort of not, they don't play such a central role because we just know everything there is to know about. And there's another very interesting basic space, which is the sphere. And we could ask about homeomorphisms or diffeomorphisms of the sphere. And it turns out we also don't know these, but we know them relatively to the two characters I introduced above. So if I have a homeomorphism of the sphere, there's a fiber sequence where I evaluate what happens at one point, say the North Pole. And then the fiber is the stabilizer of the North Pole. But if I have a homomorphism of a sphere that fixes the North Pole, that's exactly the same as removing the North Pole and taking a homomorphism of the compact by 1 point clarification. So that is exactly just homomorphisms of space. Similarly, if I have diffeomorphism of a sphere, I can do a slightly different thing, which is I can fix a point, or I can act on a point and on a tangent frame of that. That gives you a map to the D plus first orthogonal. And the fiber turns out to be diffeomorphisms of the disk. That's basically because if I fix the North Pole and I fix the tangent space of the North Pole, I can sort of do the real blow up. That's a diffeomorphism of this well. So the sphere is perfectly interesting as well, but somehow we'll neglect it a little bit because understanding anything about these spaces, top D or diff of a disk, will up to some spaces that we convince ourselves that we understand very well, like the sphere in the orthogonal group, is sort of the same kind of. There's one further thing. So everything so far has been quite elementary, and this is not very elementary. This is the so-called fundamental theorem of smoothing theory, but it only involves characters that we've introduced so far, and it says the following. Which seems to be a sort of general principle in the topology of manifolds, that it's quite difficult to understand the symmetries of some specific manifold, but it's often quite plausible to understand the difference between two kinds of symmetries. In particular here, the difference between homomorphisms and diffeomorphisms of a disk turns out to be the D-fold loop space of the space of homomorphisms or diffeomorphisms of a Euclidean space. So this involves all the characters from the previous slide that weren't to do with spheres. 4 characters, 2 of them were just known, right? Homomorphisms of the disk was contractible, and diffeomorphisms of RD was just homotopy to the orthogonal group. So basically, this says up to spaces which are known, top D is roughly the same as diffeomorphisms of a D disk, which is roughly the same as homomorphisms of a sphere, which is roughly the same as diffeomorphisms. And if you try to make this not quite roughly, but more precise, then you might get, there's some extensions maybe you have to solve or something, but sort of roughly speaking, computing something about any of these spaces is the same as computing something about all the others. So the goal of these talks is to talk about one, hence any of these kind of spaces, and what we can say about their topology. What would it mean if the space of diffeomorphisms of a D-disk were contractible? If you just go through all these fiber sequences and equivalences I wrote down, what it tells you is the following. It tells you that homomorphisms of a sphere is the same as diffeomorphisms, is the same as the rigid diffeomorphisms, i.e. the isometries of the sphere. One. And it would say that homomorphisms are the same as diffeomorphisms of Euclidean. Okay? And all our experience tells us that this is true. All our experience tells us in all the symmetries of manifolds we can think about this is true, and that's because in all the dimensions we can really think about, it is true. So for the one-dimensional disk, you can prove yourself is contractible using linear interpolation. For the two-dimensional disk, it's limit of Smale, and for the free disk, it's a so-called Smale conjecture. Had to prove it's a more recent Ricci flow proof like that in Kleiner. And these are the dimensions that we have somehow native experience of. And so we're forced to think that all these things are true, but it turns out that it's never true in any of the dimensions. So in every dimension bigger than 3, none of these equivalences are true. The one that's normally studied is the one that I write is the diffeomorphism of a disk, but it's just equivalent in all these other equivalences being or not. And so this has a very long story. I mean, Milner's paper on exotic 7 spheres already says in its penultimate line, oh, incidentally, this means that the group of diffeomorphisms of the 6th disk is not contractible, is not connected, sorry. In particular, not contractible, because it's not connected. There's lots of work in between, but a few years ago, Watanabe showed that in every dimension, starting for in a uniform, sort of for a uniform reason, they're just not contractible. We just know some, in fact, they're not even rational. Just know some rational. And I'm going to be talking about this kind of thing throughout all the lectures. You're not supposed to appreciate it immediately. It will take some time. So my point of view is that algebraic topology is, to the extent possible, about calculating things. And so I don't just want to know what this space is not. I would like to know what it is. So what are, if it's not contractible, then what is it? So can we give some sort of answer? Of course, it could just be some new primitive object that cannot be described in any other way. But you can still ask for calculations of, for example, its homotopy groups or its homology. So as I said, so this is my goal for these lectures. So today I want to explain some classical results about these kind of spaces, and then some more recent ones. Explain the statements of, and then propose a sort of conjectural picture for what diff of a disk should look like in all dimensions, or big enough dimensions maybe. Then I want to describe the main recent tool that we use to study these kind of things. It's a so-called Weiss fiber sequence. This is completely elementary and not very difficult at all. It's just a brilliant idea of Michael Weiss that it's a good idea to do it. What it does is it relates diffeomorphisms of a disk to diffeomorphisms of very complicated manifolds and self-embeddings of very complicated manifolds. And those two things can be studied separately using different methods. And then diffeomorphisms of a disk is somehow the difference between those. To carefully take the difference to see what it is that you prove. So that kind of strategy is what I want to explain over the course of the next talk. And then to make this real, then I need to explain to you why we can say anything about diffeomorphisms of very complicated manifolds, and so that would be roughly the content of the kind of strategy. For proving things, it's completely essential to think about diffeomorphisms. You cannot think directly about a homomorphism. Somehow, I don't know any theorem about homomorphisms that you prove by thinking about homomorphisms. What you do is you use smoothing theory to change it to a question about diffeomorphisms of a different manifold, and then you use the smooth structure and various things available. But on the other hand, it turns out that it's much cleaner to state what it is that you prove using homomorphisms. So I'll try to state things using top D, but in the next two lectures, it will be clear that what we're really doing is things about. And also, the way that I'll state things is basically going to be in terms of rational homotopy groups of the classified space. Okay. So if you don't know what the classified space is, not so very important. It's just the homotopy group shifted in index by one. But I'll phrase everything in terms of what we know in this sense. This is in some sense a shadow of maybe what we really know, but it's a very communicable way of explaining progress. Okay, so let's first do a warm-up to studying top D, which is studying O of D, which is diffeomorphisms of D-dimensional Euclidean space. There's also orthogonal matrices. And of course, if you have a D+1 by D+1 orthogonal matrix, I can record its last column. That gives me a unit vector. I've written that to SD. And the fiber is OD. It's the possible complementary basis vector. So OD+1 or OD, the homogeneous space, is just SD. And we know homotopy groups of spheres is still a big problem, but we do know quite a lot about homotopy groups of spheres. In particular, we know that the homotopy groups of a D sphere below degree D are zero. It's a very basic result in topology. So in particular, that means that the OD and OD+1, their first few homotopy groups cannot be different, if they differ by the low homotopy groups of D sphere. And a bit of a less elementary thing is that the rational homotopy groups of spheres we all know, and we've known for a very long time, of course. I say it's less elementary, but only relatively speaking. I won't write down what it is, but you can imagine that if you know the homotopy groups of spheres rationally very well, and you know this identity, then you can do some sort of induction to compute the homotopy groups of code. Of course, you have to do something along the way, but this is the formula that you get. So formulas like this will show up quite a lot today. So let me go through this one a little slowly. So my notation here means, so Q square bracket something means a copy of the rational numbers in that homological or homotopical degree. Okay, so I'm writing down the first start, so I'm writing down all the homotopy groups as a graded vector space. And so what this is saying is that there's a copy of the rational numbers every 4 degrees, so 4, 8, 12, and so on. And then we start at some point. We stop at some point, D minus 1 over 2. And then there's one more phenomenon that can happen, which is when D is even, there's an extra copy of Q in degree D, and when D is not even, there's not an extra. And these are not just somehow symbols for Q, they have some geometrical meaning. These ones in degrees 4i correspond to Pointryagin classes, which you might have seen in course on characteristic classes. And this one in degree D, which only exists when D is even, corresponds to the Euler class. So these are somehow, it's not just some abstract isomorphism, they're meaningful elements. So that is somehow what it looks like, and I'll draw it as a chart like this. So there's this sort of parity distinction. The blue classes here correspond to this Euler class. They're in degree, hopefully I've drawn it correctly, but in degree exactly equal to the dimension. And I'm drawing the dimension of the Euclidean space horizontally and the homotopical degree vertically. Okay? So just have a look at this. There's going to be many charts analogous to this one, and to understand them, you have to understand the one that they're analogous to. So all these orange dots correspond to these contractibility classes. They're in every 4 degrees, and at some point they stop. And then it's an additional feature in the even dimensional case. There's also these Euler classes. And that's a complete answer to what are the rational homotopy groups of diffeomorphisms of Euclideans. Okay.
So you don't mean diffeomorphisms, you mean orthogonal.
Well, it's for you, I mean,
well, okay.
For the whole Euclidean space, that's the same thing, right? So I want to give 3 ways in which this picture cannot be the true reflection of what happens with top D. And they're sort of increasing sequence of modernity. So the classical way that one studies diffeomorphisms of some manifolds is via the sort of surgery theoretic program, if you like, where you assume that you can understand the homotopy self-equivalences of that manifold, which of course for a disk is very easy because a disk is contractible. And then you promote that to the so-called block diffeomorphisms using surgery theory, and then you try to promote that to actual diffeomorphisms using so-called pseudo-isotopy theory. And all of these steps are typically quite difficult. Even the first one is quite difficult for manifolds that are not a disk. But the third one is not just quite difficult, it also has an intrinsic theoretical limit. It can only tell you of what happens up to degrees about the dimension of the manifold over. That's what's built into how it works. That's the so-called pseudo-isotopy theory. So the other tools, in principle at least, give you complete answers to the question that they answer, but the final one only gives you an answer. So you can apply this program to the disk, and then you can use this Morley equivalence that I mentioned to rephrase what you've done in terms of top D. And that was done by Fowler and Xiang. And you get the following formula, which is analogous to the formula that I had previously. So rational homotopy of B top D, there's classes every 4 degrees. If D is even, there's another thing, there's another class that corresponds to the Euler class. But if D is odd, there's some new stuff. And this new stuff is also not just from abstract symbols called Q. The things in degree 4i are the so-called topological contractibility classes. The thing in degree D, in the even case, is still the Euler class. And the other classes, it turns out, correspond to the algebraic K theory of the integrals. In fact, the Euler class does as well. It corresponds to K0, and the other ones correspond to K in degrees 1 or 4. So the totality of this stuff here is exactly the rational algebraic K theory of the integrals shifted up by D. Turns out there's an involution on that space, and the parts that you see in the even and odd dimensions correspond to the eigenspace. Trivially on K0 and the axis of -1. So this calculation is valid in the range in which this theory applies, which when we do the translation is 4/3 times that. So it's already shown that something different is happening to BOD, namely all this stuff that corresponds to higher algebraic K theory. That's a new phenomenon that didn't happen for BOD. So the other new phenomenon, in some sense much more recent, in the 90s, was a definition by Kontsevich of so-called configuration space integral classes. So this was a new kind of characteristic class for disk bundles. In fact, it's framed disk bundles, but that doesn't make a huge difference to the story. And he explained how if I have a bundle, I can look at all associated bundles of configuration spaces and certain compactifications of them. And I can integrate certain naturally defined differential forms. Typically, these forms configuration space is a manifold with boundary, so the forms you get when you integrate them need to be closed. But you show that you can match up the boundaries of all these configuration spaces in a careful way to get modified classes. And the combinatorics of how you should match up those boundary strata are governed by certain graph. I'm going to talk about graph complexes a lot more later, but Watanabe analyzed this in the sort of top or in extremal degree, which is when the graphs are trivalent. That means you can't possibly expand any vertices in any way. And using that, he rephrased in terms of B top D, as I like doing, he proved the following thing. So in any dimension, at least 5, there's a surjection from a certain homotopy group of B top D, some index that doesn't matter, to a certain vector space of trivalent graphs. And the vector space depends on the parity of D. The way I've written it, it doesn't visibly depend on it. I'll come to that. What it's given by is you look at graphs, trivalent of Euler characteristic minus R, so that means they have R minus 1 groups. And then you declare, you take linear combinations of such graphs, and you declare them to be trivial if they differ by this local kind of group, so-called IHX. And you also declare them to be equivalent if they differ by certain signs, which I can't explain to you because I haven't told you the true definition of what goes on the left-hand side. Graphs come with a little bit more data, like orientations and various things like that. And changing orientations introduces signs. So that's where the sign minus 1 to the D enters within that convention. And these vector spaces you can put on a computer and calculate how big they are, and then they're not the zero vector space, typically. So the dimensions are dependent again on the parity, but they're not typically 0. And so his theorem is that this subjects onto that group, and so whenever the target is not 0, this domain must not be trivial. And if you just do a bit of numerology for yourself, like if you picked one of these numbers up here, where R was about 6 or so, then this is about 6 times the dimension. So that's well outside 4/3 times the dimension. It's the range where the previous stuff applied. And it better be well outside that range, because these, the degrees, they're not the kind of classes that you have. They're just some new phenomenon. So they better not be expressible in terms of the stuff that's ordered. So that's the second story, and I've sort of done Watanabe a small injustice here because I wanted to phrase it in terms of B top D, and so I said you should start in dimension 5. But what he proves is actually a statement about diff of a disk, and he proves it starts in dimension 4, and maybe the fact that it works in dimension 4 is the biggest highlight of his result, because it proves, I mean, it sort of finishes completely this question about which of these diffeomorphism groups are when I'm not contractible. But the translation from diff to top is not legal in dimension. I'll state it as a statement about. So that's the sort of second short story. And the third one is the one that was very motivational for me and for my collaborators is Michael Weiss. So I've just recapped here calculations, the complete calculation for BOD and the calculation in degrees 4/3 D, B top D. And it's a bit difficult to formulate what Michael did in a reasonable way, but let me try. So for big enough dimensions, something like 50 something is what comes out of his method, but let's just say for big enough dimensions, and for certain numbers I bigger than D minus 1/2, there are classes that are not trivial that belong to this this 4i copy of Q. So this is a bit subtle here, but the point is that this sum stops at some point. And this sum I didn't deliberately stop at some point, but I only claim the equivalence up to some range that's way below that point is anything. So the content is that these copies of Q4i stay being even though this calculation may not be exact, we stay being non-trivial in the left-hand side, way beyond where this sum stops. Okay. Now it's a bit difficult to put it in this sort of way. In a while, I would draw some charts of various things, and it will be a little more understandable. It's quite a results.
So should we think of this as there's some kind of exotic manifolds or exotic homeomorphisms that can't be smoothed, or what?
Families, I suppose you would say, homomorphisms.
Oh, right.
So there's a 4i dimensional family of homomorphisms, the 4i being enormous. And yes, you cannot, even undertaking powers of it under sort of in homotopy, you can't. In particular, I mean, another way of saying it, and indeed the way Michael Weiss did say it, is that you have contrarian classes in cohomology BOD, and you have rational contrarian classes in cohomology B-top-D. But in BOD, they're defined in a very hands-on way, and it's completely obvious that large contrarian classes are zero on small dimensional bundles. Topological bundles are defined in a very roundabout way. It's completely not obvious that large contrarian classes are zero on small dimensional bundles. And what this is saying is that they're not. Now, relatively, you can have a 6-dimensional bundle, in fact, and you can have very large contrarian classes, which are not. But as I said, this is the thing that's closest to what I'm going to talk about in all the lectures, and so somehow this will be a little more clear. So, we'll talk about some patterns. So these were just 3 phenomena that seemed to happen outside of, well, the first one was the classical Yang calculation. The second one was this new phenomena of configuration space intervals, which seemed to give something. And the third one is this discovery by Michael Weiss that contrarian classes seem to extend beyond where we're used to them extending in vector bundles. So inspired by a certain idea that Michael Weiss introduced in proving his theorem, Sander Kubers and I tried to just use that method, not to just show that certain classes are trivial or non-trivial, but to just calculate completely what we get. Or to the extent possible. And what we proved in that direction, or here's one formulation of what we proved in that direction, which is, here's one way to say it, the dimension starts on 6, even dimension starts on 6. The Fowler-Yang answer is correct, not just up to 4/3 times d, but if you just exclude certain ranges of degrees. Okay? And you can look at this formula for the range of degrees. The dimension is 2n, so this is basically saying it's a range of degrees that's roughly s times the dimension, where it is, and its width is roughly in the order of s as well. So they move up with s and they get a bit wider with this. But if you exclude those ranges of degrees, then it's classical calculations. So this is incomprehensible to us like this, and so I have to draw a picture. Okay, so this is what the picture looks like. So the orange dots are these topological contrarian classes, which are predicted by Fowler-Yang. The blue ones are this Euler class. This black dotted line going on here is the classical Fowler-Yang or inclusive stable range. So below that is what was somehow the sort of null hypothesis of what maybe the whole thing is supposed to look like. And what we say is that this pattern, firstly, continues above that line, in fact, well above that line. And then there's some new phenomena that show up, maybe in these bands. And outside of these bands, you just see the pattern reproduced. And inside the bands, maybe something else happens. But the bands are like a question mark. So in some situations, I've drawn a dot under a band, which is where we have some other reason for knowing that one of these dot classes is non-trivial there. But in principle, there's other classes as well in the band that come from whatever. And for example, not just in principle, but in fact, because the classes that Watanabe found have to be somewhere in this picture. And it turns out they all lie roughly along the middles of these bands. Right, so there's some mechanism that lets me know that there are sometimes dots on the bands. Roughly speaking, this is what we do. So the other, that was about even dimensional Euclidean spaces. So we wanted to do a very similar thing for odd dimensional Euclidean spaces. So this was a collaboration with Manuel Weiss. We tried to do, in some sense, a similar thing, but we were deliberately using different methods. So the kind of theorem that we get is a little different in flavor. For example, it's not something about bands, it's just an absolute calculation, but in a much bigger range than the classical one. About 2.5 times d, 1.3 times d. And what it says is you get what Fowler-Yang found, and you get one new guy. Q in degrees 2d minus 2. And again, it's not an abstract calculation. These all have a meaning. These ones in 4y are the contrarian classes. Second sum and all these classes coming from algebraic K theory. And this new thing turns out to be exactly Watanabe's class for this trivalent graph, which is the letter theta. It's a trivalent graph. and that represents an element in Mark's language. And it has exactly this degree, and that's somehow new or a new phenomenon. And this is a similar picture, except that now there's just a hard cutoff where we don't calculate. It's very similar. There's this pattern of Pontryagin classes. There's these algebraic K-theory classes in blue, and then there's a new kind of triangle class, which is really difficult to distinguish, but that's this trivalent graph picture that happens in all these directions. And again, the black dotted line, this is the classical region where you wouldn't see, for example, this triangle class at all. So these are some patterns. Of course, one imagines that this band pattern happens here as well, except that we didn't calculate far enough to really see it. In some sense, we did. This triangle is somehow the first band. That's the first place where the pattern is not just the dots. But we didn't calculate further to find the next one, I suppose. So this you can sort of view as experimental data for the question of what is going on. And we've calculated as much as we can, and somehow you want to now come up with some kind of principle that would explain this observation. So here's what it looks like to me. So it looks like to me that the homotopy groups of B top D are the basic pattern that Fowler and Xiang found, and somehow superimposed on that is some collection of new phenomena that happen on sort of different wavelengths. That's somehow the fact that these bands have different slopes. So in a given column, let's say if you go high enough up, all of these bands will start overlapping with each other, and there'll be some sort of interference probably, and the answer will be very complicated. But along each band, you can expect maybe that somehow the same thing is happening all the time. It does the degree in which it happens depends on D. But the fact that it happens does not, maybe it depends on the parity of D. Sort of saw this even and there's a very good candidate for what this superimposed phenomenon should be. In fact, I said that like you can imagine these bands interfering with each other. The conjecture is that they do not interfere with each other. And what this new phenomenon should be is so-called conservative community graph model. So I'll say a little bit about this, but the formula, some completely algebraic thing. The formula would be that this is just the answer. Pontryagin classes plus whatever you get from algebraic K-theory in the even-dimensional case, just plus a copy of the L-loop graph homotopy starting at loop order 2. The conjectures of this is just a complete answer for what is the rational homotopy of E of homeomorphisms of E. So let me tell you a little about this GC thing.
But since you're on this,
yep.
In theory, this could be the last term, your conjecture, for any given dimension. It could just be calculated on a computer. Purely combinatorial?
Yes, it's purely combinatorial. So let me give you the definition now, and we'll see a bit about our sort of definition. See what it is. So it's just a chain complex spanned by connected graphs that have Euler characteristics. Whatever. They have L loops. So that means Euler characteristics 1 minus L. And we can say rational linear combinations of things. So a graph contributes to a certain homological degree, which just depends on its number of edges and vertices. And it has a differential on it. And the differential is given by summing of all ways of contracting an edge. So you, on a given graph, you sum over all ways of contracting a single edge. And there are some rules you can impose here. Like I said, they had L loops, so you can't contract an edge that is a loop, because then it doesn't have L loops. Not have to do that. But you're allowed to contract all edges that make sense. If you want to check that D squared is 0, so that this really is a chain complex, you will discover that the thing I said does not work, because you need to have some signs in order for things to cancel out when you take D squared. And it turns out there's, so here onto the minus. And here I said that there's basically 2 conventions to have. And that corresponds to, the 2 conventions correspond to somehow -1 to So I'm not going to tell you what they are. They all involve decorating the graph with much more data than I can here, like something of the following order, like a total order of the vertices, a total order of the half edges around each vertex, maybe an orientation of each edge. And then you say, well, if you reverse the orientation of an edge, then in the D even case you do nothing, and in the D odd case you put a -1. And if you reorder the vertices, then you pay some sign as well, and so on. But there's two basic conventions in how, and they're really different chain complexes. It's not just a convention; they're just different objects. But as you see, they're completely elementary somehow.
How many loops are in that chain complex? What would you allow to collapse?
There you allowed, so okay, you like that, I think anything. There's no actual loops in that. So loop just means that edge whose start vertex and end vertex. I know this round thing looks like a loop, but it's not, it's two edges that go between two. So you couldn't collapse this one and then later collapse the next. Once you collapse one of them, then the next one. Right, so
I'm sorry, so why
Yep.
did you include that?
just another graph looks like this. I guess I could have drawn a more representative example. So anyway, the graph multi does the homotopy chain complex, and these, as Benson says, you can stick on a computer and see what you get. And what you get, so I've ordered it by loop order, and then there's these two cases of even and odd parity. For reasons I cannot say, the odd one always seems to have more homotopy than the even one. It's an observation of fact. And the convention is the same somehow. If you want Q square brackets, the degree in which you're substituted. And we know a little bit more than this. We know up to loop order 10 as of last year. So it's calculators of Willowacker. And it gets more complicated, but I mean, the answer gets more complicated. But the calculation gets extremely more complicated because there were a lot of graphs with 10 measures, for example. So we know up to loop. So if one accepts the conjecture that I made on the previous slide, then this is a complete picture, roughly speaking, apart from, I think, up in this corner. It's maybe not quite right, but roughly speaking, this is a complete picture of the rational homotopy groups that we talk to n, if you believe it in that.
You'll tell us what these graphs have to do with commuters with this.
In a minute, yes. So you notice that, so there's some color convention I'm using here that I haven't told you about. It's actually quite useful to remember the fact that pi 1 of B top D is Z mod 2. You can do a reflection. I mean, another way of saying it, pi 0 of top D is Z mod 2. Reflection. And so all the homotopy groups have an action of Z mod 2. Pi 1 of the space acts on all the higher ones. So if you work rationally, in fact, you just have an involution on all the homotopy groups inside. And the colors are just the eigenspaces for that. So all the, I guess, orange must be the +1. So for example, the fact that the Euler class is in blue is the fact that when you reverse the orientation of a bundle, you indeed negate the sign. These other things up here have the same property, or some of them have the same property, and some of them don't. Turns out that the band of slope R transforms like -1 to 2. So that would be a complete sort of calculation picture of what these rational homotopy groups look like. But as Benson says, somehow maybe we don't just want to describe a list of vector spaces. We want to give some more conceptual description of what's going on. So the last thing I want to explain today is maybe a space level interpretation of maybe what's happening. And there's a very plausible tool for describing what's happening, which is the so-called orthogonal calculus introduced by Michael Weiss. So many things that this builds on, in fact, introduced by Michael Weiss. So this is a calculus in the sense of Goodwilly's calculus of functors, or embedding calculus, which we'll talk a lot more about in the next lectures. And let me give you a brief idea of it. So this involves not thinking about one top D at a time. You can think about all of them together. And you should think, in fact, about a functor that sends a vector space V to V of homeomorphisms of that vector. And to be careful, vector space means real vector space, and in fact, it means real inner product. So that's a functor on the category of inner product spaces and inclusions. If I have an inclusion of one inner product space V into W, and I have a homomorphism of V, I can extend it by the identity on the orthogonal complement of V. And that's why I need to say inner product space. That's a functor. And the game is to consider functors from this fixed source category, bidimensional inner product spaces, to spaces, or maybe I said base spaces here. To consider functors like that as though they were functions of one real variable, and to develop a notion of Taylor expansion. That's the game. So to talk about, so what is the Taylor expansion of function? It's the best approximation to that function by a polynomial degree by K. And so we had better say, well, I said that already, we'd better say what polynomial means. So how do we define polynomial? We say, a function is polynomial of degree K if when I take its derivative, K plus 1 times its trivial. So as long as I can say the word derivative, then I can make the analogous definition. So I define the derivative to be the following. Given my functor f, I look at f of v. V has a canonical map to v plus r, map of inner product spaces, and I take the homotopy fiber of that map. Luckily, I said base spaces, and so I take homotopy fiber over the base point. And I call that the derivative, the first derivative. And then I say the functor f is polynomial of degree r if, when I do this r plus 1 times, I just get the constant functor, which is contractible. Okay, that's the definition. In functors are not functions. And from some points of view, that's a difficulty, but from other points of view, it's an advantage, because when we talk about approximating smooth functions by polynomials, we have to say what it means to be a good approximation. But with functors, there's no choice about what it means to be a good approximation. There's a category of all functors, there's a subcategory of all polynomial functors, degree at most r, and good approximation means localization universal. That's meaning category theory. And by general blah blah, there is one. So any functor has the best approximation by a polynomial functor degree at most r. Let's get the map to it. Of course, that's the other difference between functions and functors, that two functions are just equal or not equal, or they're similar or not similar, whereas for functors, you have to tell me what the map is between them as well. You can't just take two functors and ask how simple. So any functor has the best approximation, and of course, the best approximation by something of degree 1 is better than the best approximation by something of degree 0, and so they assemble into an inverse. This is all super formal so far, but then something non-formal happens, which is that there's this is some corrected formula that I can talk you through slowly. There is just a complete description of what the difference is between two stages in this table. So you should think about this as being a classification of the homogeneous polynomials of degree n. What is a homogeneous polynomial of degree n? It's something that's polynomial of degree n, whose best approximation by a polynomial of degree n minus 1 is 0. That's exactly what means the one step. I guess I said n, but I meant to say r. And the non-trivial theorem is that they're just a complete classification. All you're allowed to do is the following. You take your vector space V, you tensor it with r to the little r, and you one-point compact it. That gives you an enormous sphere, and because I tensored with r to the r, it has an action of the r orthogonal. And then you're allowed to take the action of the r orthogonal group on any spectrum, and you're allowed to tensor them together spectra. And then you're allowed and obliged to go to spaces by taking this as the. And so this theta FBR is somehow, it's like the coefficient, like the R coefficient of the. And it's just a fact. It's not given the stuff before, it's not even a choice, that these homogeneous functors are described by spectra with an action of the R orthogonal. That's what a homogeneous functor. It's exactly equivalent to the data, a spectrum with an action of the R orthogonal. So that's a very brief introduction to this orthogonal calculus. How are we supposed to see configuration spaces entering the picture? Well, we saw configuration spaces entering the picture already, and you can say which is invariant. And that maybe suggests that containment is invariant because you have a bundle of disks. You look at the fiber-wise configuration spaces of some number of points in this, an arbitrary number of points in this, and then you do some combinatorics of what the boundary starts. In other words, you think about what it means when points come very close to each other, or maybe collide. So maybe we should study top D by studying its action on the space of all finite configurations. And we shouldn't study the action on one configuration space at a time, probably. That's somehow too naive. We should remember the fact that on the configuration space of K points, if two of those points are very near together and very far from the other ones, then a homomorphism has to keep them very near together, very far. And so in some sense, it has to extend to the borderfication. Speaking not true, but in some sense it's true. It would be true if I said different. And so we should remember the fact that points can come together, and maybe the fact that points can collide. A good way to do that is to not think just about configurations, but think about the algebraic object that governs configurations in RD and all ways they can collide. And one encoding of that algebraic object is the little d disk. So this is invention of Peter May. And when you think about it as little disks, it's not really obvious how top D acts, but there's a different model for it, which is the so-called ultimate person software, which is literally points in the plane. It's something like that. And any homomorphism literally gives you a symmetry of this one. And so, in other words, you get a map from B of the group of homomorphisms to B of the group of automorphisms. And here it's important to interpret automorphisms in the maximally homotopical way. I don't mean literal maps of operators which are literally reversed or anything like that. I mean homotopy self-equivalences. So this is something you can do. And I said we were going to study B top D by studying really B top blank, like a collection of all B top Ds of all Euclidean spaces and all possible maps between them. Well, we should probably do the same thing on the right-hand side as well. Sorry, before that, the homotopy groups of the automorphisms of the rationalized ED operator is this conceived graph. In the first thing a few years ago. So that's somehow a very good sign that it, or that's meant to be how it fits with the and let's assume for a minute that somebody can make a functor from inner product spaces to spaces that assigns to a vector space V, B of the automorphisms of the little V disks. And what this means is V is an inner product space, it has a unit disk, and you make the operad of embeddings of that disk into it. So that is abstractly the usual disk of that dimension, but this is a sort of coordinate-free way of describing what it's doing, and in particular, it makes it clear that OV activates in that. So let's assume we can make an orthogonal functor like that. Then here is a rephrasing of the calculations that I've been giving you in terms of these derivatives, in terms of orthogonal derivatives of the top. So all these conjugation classes that show up in a degree that does not depend on the dimension, they correspond to the zero derivative. They somehow give Q every 4 degrees. All the stuff that corresponded to algebraic K theory, it showed up in degrees that were D plus a fixed number. And from that point of view of this calculus, that means it corresponds to the first derivative because it grows like 1 times a day. And so that somehow would be a calculation of the first derivative. And this band picture suggests that all the higher derivatives are much simpler than these first two. They have finite width, they have finitely many homotopy. Finitely non-trivial one. You can go and assume you can make an orthogonal functor, and you can look up the calculations that they've done involving graph morphology, and you can intuit what the derivatives of this functor BA would be. And what you discover is that the zero derivative will be 0, which looks very bad for being an approximation to the left-hand side. You can calculate that the first derivative, well, if you want to be fancy, you can say it looks very much to me like negative cyclic homotopy. But it's a spectrum that has one homotopy with Q in every negative eigenvalue. There are many spectra that have that property, but I want to say I think it's negative cyclic homotopy. One example. And all the higher ones will be described by this L loop. And it strikes me that I didn't say this when I started talking about homotopy, but for a given loop order, there's only finitely many non-zero homotopy. Because the worst you can have is a trivalent graph, which is like you can contract over here. And the worst, or the other extreme, is you can have like a one vertex graph with lots of loops, and you can't contract anything. And everything sits between those two things, and those are known loops. But outside of that, you can't have any graph. So they all have finite minimal width. And indeed, they would describe the derivative. So if you want to think about this as being an approximation, the first two rows of this table will maybe make you think it's not a great approximation. 0 is not a great approximation to all these properties of Q, and negative cyclic homotopy is not a very good approximation to K theory. For example, negative cyclic homotopy is in negative degrees, positive degrees, so then it's got a bad approximation. But the proposal I want to make, and which I firmly believe, is that that's all that goes wrong. In particular, all the higher derivatives are just the same. So the proposal, and this is just a reinterpretation in some sense of the conjecture that I said several slides ago by now. Right, the conjecture is that all the higher derivatives are equivalent. And another way to say that is that if you compare BT of RD with BA of RD, they're probably not very similar, but the difference is exactly the same as what's accounted for by the difference between the 0th and first. So one way to phrase it is that this kind of square is rationally a Cartesian square. So that's somehow saying why graph complexes show up at all. It show up because this attempt to calculate B top by letting it act on finitely many points is not a perfect model, but it differs by some known stuff. I should point out that the right-hand column, we know everything about this. Q is every 4 degrees, K theory, 0 and negative cyclic homotopy, and we know what the math is. So as I said, this proposal is in some sense formally meant to be roughly interchangeable with the conjecture that I made a while ago, but is a bit more conceptual. I think it's a little bit remarkable. Oh yeah, but before that, we have some evidence here. The reason that Manuel Pranek and I computed up to 2.5 times the dimensions is that we needed to get up to 2 plus epsilon times the dimension. 2.5 to that be what we could get. And that was because knowing up to 2 plus epsilon times the dimension is what you need to completely compute the second derivative. We did, and you get a certain thing, and you can check that it's what you get for B. So we've checked this proposal on the first entry of your case. And it's fairly, let's see what the answer is. I mean, they're slightly rich objects, right? They're spectra with an action of the group O2. That's what these kind of derivative objects are. And it turns out that both of them are spacer maps from the circle to the minus 1 state. And that has an action of O2 by the unit factor. So that's what both sides are now. So it's not a super complicated spectrum, but it's complicated enough that it would be a bit of a coincidence that these are just equivalent ones. Right. So yes, so finally, so this, I think if this proposal is true, this would be kind of remarkable because it brings together many things which some of them we knew were related to each other, but some of them we really didn't. I mean, the question is about homeomorphisms in Euclidean space. It relates to algebraic K theory and L theory I didn't say it this way, but all these copies of cumulatively 4 degrees, which you all will recognize as being B top, being homotopy of B top, so it's the stable homotopy of B top D as D goes to infinity, and is also D mod top, which is quadratic Elkin. So you can think of that term as really being a hidden instance of quadratic Elkin. K-theory explained how it shows up along the way, and somehow the slogan is that this first derivative contains all the K and L theory information. This BA contains is basically built out of this graph cohomology, and you should glue them together by pulling back along this thing, which is exactly negative significance. And somehow that's how you're meant to assemble the classical sort of K and L theory part with the maybe less classical graph complexes part. They're meant to be glued together along cyclic homology. And somehow that's the only way that those two ingredients are allowed to talk. And cyclic homology, as I said, is not so terribly complicated. So in fact, they glue to each other in a very soft way. But I think the collection of things involved here are kind of surprising. So that's the end of that, I think. Probably. What I want to do with the next talks, which will be on a blackboard, is to explain this basic band pattern. So I want to explain why this is in any way plausible. Okay? And the full proof of this is I went back and counted. It's sort of stretched over maybe 5 papers, which are maybe 300 pages in total or something. So obviously I'm not going to fully succeed in telling you everything. But I want to somehow make it plausible that this sort of pattern happens. And I think that's the main somehow insight, that there is this kind of basic decomposition. And homeomorphism groups is some basic underlying pattern with this and superimposed. So that's what I want to try to explain over the next talks. And it will be, that's one goal if you like, but the real goal is to explain to you some of the methods that we use, which in principle can be upgraded to calculate what happens in this, not just to show that it's equal to this underlying pattern modulo some unknowns. In principle, soon we'll calculate the unknowns. Okay, thank you.